Particulate matter is a term that is used to describe both solid and liquid particles that are suspended in the air. These particles can be comprised of dust, dirt, soot, smoke, and various other chemical compounds. They come from a variety of different sources, including vehicle, shipping, and industrial emissions, agriculture, construction, and wildfires. Particulate matter is often reported in two categories, PM10 and PM2.5 microns in width. This is where the danger lies. Because particulate matter is so small, it can penetrate your body's natural defenses and become lodged in your lungs or diffuse into your bloodstream. This can cause negative health effects including asthma, bronchitis, and decreased lung function. California has a diverse demographic and large population, which consists of roughly 39 million people. It also has an extensive transportation infrastructure with 11 major ports, 6,800 miles of rail lines, and over 394,000 miles of roads. With such a big population and massive transportation system, there is a growing concern about increasing asthma rates due to the proximity of traffic. It is this environmental health threat that I will attempt to validate with my own spatial analysis. The first step to answering my research question is to collect and prepare transportation data. I then use the reproject tool to project my port, rail, and road input layers. This will minimize distortion and preserve shape and area measurements within my subsequent maps. After the input transportation layers were reprojected, I then ran the Euclidean distance tool in order to show distance in meters from each type of transportation line across the state. Next, I used the cell statistics tool to combine the Euclidean distance layers and calculate minimum distance in meters from any given transportation line. This output layer provides the proximity component to my analysis. Then, I used the zonal statistics as a table tool to determine the average distance to a transportation line within each census tract. This tool summarizes the values of a raster layer within the zones of another dataset and report the results as a table. In the output table, each individual zone directly matches to a corresponding census tract. The final step is to join the zonal statistics output table to the census tract and asthma rate shapefile. This map combines the average distance to a transportation line and compares that to existing asthma rates by census tract. Upon completion of this analysis, I was able to conclude that there is indeed a spatial relationship between emergency department asthma rates and proximity to transportation lines at the census tract level. Furthermore, I also determined that there is a positive correlation between asthma rate and distance, where the closer you are to a transportation line, the more likely a population is going to be exposed to traffic emissions and results in higher asthma rates. The methods in this study are easily extensible. Environmental managers and city planners can use this information to analyze other populations, like those living in poverty, or sensitive individuals, like the youth or elderly, in order to prevent these groups from experiencing disproportionate traffic emission exposures. Managers and city planners can also use this study to encourage the use of public transportation, which would help reduce particulate matter emissions in the long term. Immediate steps can also be taken to improve air quality. This can be done by planting trees in communities that are close to transportation lines. Trees can help filter airborne pollutants and improve nearby air quality for residents. Ultimately, any combination of these management efforts will improve the health of the environment and the health of its citizens.